Okay, guys, so now what we're going to do is talk about what is called a p-value. So the definition for a p-value is a probability of obtaining results more extreme than the observed results, given that H sub O, the null hypothesis, is true. So a p-value is a probability. So that's the first thing that we have to remember. P-value, p, hence the name p-value for probability. So it is the probability of obtaining results more extreme than the observed results, given H sub O is true. So this is a little bit tough to wrap your mind around, but I feel like once you get it, it's not bad. So here's what I want you to imagine. H sub O, the null hypothesis, is true. So whatever somebody has claimed about the mean is truly the actual population mean. So what happens is, let's say, I don't know, let's say this is number of chocolate chips in a cookie, okay? Let's say that the real true mean number of chips in a cookie is 30, okay? But let's say we're doing this experiment and we only get 12 chips in a cookie, okay? So 12 chips, that's less than average, so it's going to be somewhere down here, and it's going to have a z-score that is negative, right? Because it's below average. So this is our test statistic that corresponds. It tells us how many standard deviations below the mean that we are. So this was our actual observed result. Now, where are the results that are more extreme? Well, they would be even farther from the mean. So it would be all of these values from our 12 chips, whatever that z-score is, and lower. So it's even farther from the mean. So your p-value is this area. When we talked about the standard normal distribution and the central limit theorem, we talked about the fact that a probability is an area under the curve. So we're looking for this area. Now, that's your p-value. Your p-value is this area that corresponds to your observed results. So your p-value tells what is the probability of getting a result like mine or one even more extreme. And basically, what it tells you is, is it extreme enough that it raises some red flags? Okay, is it extreme enough to raise some red flags? So we have kind of this standard idea, this standard cutoff that we use that helps us determine, what are we going to do with this p-value? So there's two things to think of. Our ultimate goal is to reject the null. Now, the way that we get to reject the null is if p is less than alpha. So alpha is what we determine kind of our cutoff value, and it's usually 5%. So remember now, this should all kind of come full circle. Remember we talked about 5%. If you're in that outlying 5%, then something's wrong. You're unusual. So if the probability of us obtaining this extreme result is so small that it's less than 5%, something is wrong. And usually what that means is maybe 30 wasn't the actual average after all. So we get to reject the null. Our other option is fail to reject. So with this, if p is greater than or equal to alpha, we fail to reject. So here's a scenario. Let's say we're assuming H sub O is true. We're assuming that it's 30 chips per cookie. Would it be very extreme, or what is the probability of us getting 25 chips? That's not very far off, right? So what would you expect the probability to be of us getting at 25 chips? that might be somewhere up here closer. So now what we're looking at is this whole area, and that's our p-value. So in that case, we have a pretty big probability. There's a pretty good chance that we would get, or we could get 25 chips. So that one does not raise any red flags, which leads us to believe, hey, maybe 30 is the actual mean. We don't have enough information or enough evidence to reject that null hypothesis yet. So what I want to show you now are some formulas and how we come up with a p-value. Okay, your p-value is essentially an area, right? And so if you think about this picture, and if you think about the notes I just did before with the critical values in test statistics, we were trying to find a value along the bottom. We were trying to find a score, if you will. So now what we're trying to do is we're trying to find an area, which means we have to go in reverse. To find your critical value, we used inverse norm and inverse t. So what we're going to use now is we're going to use normal CDF and TCDF. So in order to find a p-value, let's say that we have a one-tail p-value, or a one-tail test, I'm sorry. Then you would use normal CDF. Here is where it's going to determine if it is a left tail or a right tail. So if it is a left tail, you have to go from negative E99 up to your test statistic, because we're basing this off of our observed results, how far we are away from the mean. And then we're basing it on a normal distribution, so 0 and 1. Now, if we have a one-tail test that is a right tail, what's that going to look like? We're going to have an area over here shaded. Oh, and actually this would be negative z, because our and I should have put that up here too, I'm sorry, our z-score would have been negative if we're less than average. So over here, we now have a positive z-score because we're above average. So this one's going to look like this. Normal CDF, we're starting with our z-score, going to positive infinity. It's going to look like this. Okay, so now what about a two-tail test? Because a two-tail test, you have two values. So what you have to do is you have to figure out both of these areas. Now with this, it is symmetric because this is a normal distribution. So whatever this area is, it is the same as this area. So there's really, you could use either one of these. You could either go from negative infinity to negative z, or you could go from z to infinity. And that's going to tell you the area of one section, but then because it's a two-tail test, you have to multiply it by 2. So the same is going to be true for all of these for your t-tests, but instead of normal CDF, you would be using TCDF. But otherwise, we put things in relatively similar, except in T, we don't use 0 and 1, we use degrees of freedom. But we'll see that when we do some examples. But this at least gives you, your formulas that you need for now. And so again, the whole big underlying idea here is this is the probability of obtaining results more extreme than your observed results, given that H sub O is actually true. So if your p-value is less than alpha, you reject the null. And if your p-value is greater than alpha, you fail to reject, which